Now, one caveat to the equation I've been talking about in the past couple of slides, the amount of heat is going to be equal to the mass times specific heat multiplied by the change in temperature, is that it's only going to apply when there's one phase. And what I mean by that is if there's initially liquid, we're going to finish with a liquid. Now, what would happen if we wanted to say, hey, I've got some block of ice, it's going to be some solid block of ice, I'm going to put it in a pot, I'm going to add heat to it, I'm going to change its phase, I'm going to change its phase into a liquid, and then I'm going to keep on adding heat, and I'm going to make it boil, and I'm going to change its phase again, and turn it into gaseous steam. So let's take a look at the energy that's required for these phase changes. It turns out that it takes energy to break down the nice solid crystalline structure of a solid to make it into the more loosely associated structure of a liquid, and then to go ahead and further break down these chemical bonds between liquids, go to individual gas atoms with some speed. It takes energy to do that. Now, if I were to look at, say, just liquid water for a second and say, hey, I'm going to add some heat to it, then correspondingly the temperature is going to change relative to how massive it is, the specific heat of the water, and I can write the change in temperature. So if I were to look at the temperature as a function of heat added, so kind of Q right here, I would expect, if I only have one phase, to see a nice linear slope, and that's what I do. Same is true for when it's all solid or when it's all gas. But what happens at exactly 0 degrees Celsius when there's going to be a phase change, it's going to take energy. I'm going to add heat and add heat and add heat and add heat and break down all of these chemical bonds of the solid until now all I have is water. So in this region right here, both water and ice are going to kind of coexist. Same is going to be true at 100 degrees Celsius. There's going to be both water and steam coexisting, and I need to add heat to break down all of the bonds of my material until I've broken them all down, and then I have steam. Now, how much energy does it take? Well, here I'm talking about in kilocalories, and for the mass that I have right here, it's going to take essentially 100 kilocalories to go from 0 degrees Celsius water to 100 degrees Celsius water. To go from ice to water, it's going to take, you can kind of see, roughly 80 kilocalories. But to go from water to steam, you can see it's going to take a grand total of about 540 kilocalories. So what that means is water vapor, steam, at 100 degrees Celsius is going to have 540 kilocalories more than liquid water at 100 degrees Celsius. What this kind of means is if you had the choice to get burned by steam at 100 degrees Celsius or water at 100 degrees Celsius, go with water. So how much heat does it take? We need to introduce something called latent heat, which is kind of like specific heat only for phase changes. There's going to be some latent heat of fusion, L sub F, which is how much heat it takes to change 1 kilogram of material from a solid into a liquid, so kind of ice into liquid water. There's also going to be the latent heat of vaporization, L sub V, which is the heat required to change 1 kilogram of material from a liquid to a vapor. And kind of, I showed that was going to be 80, and this was going to be 540 on the last slide. And if we were to, at least for that particular example, kind of take a look at table 14.3, it's got latent heats for a whole bunch of materials. Let's just stick for water. And the latent heat of fusion is going to be 333 kilojoules per kilogram. Again, pay very close attention to units in this chapter. And the latent heat of vaporization is going to be 2260, which is much larger than the latent heat of fusion, which is kind of what we expect from the last slide. So now that we've introduced the latent heats, we can finally talk about the energy associated with the phase change. So again, that's going to be right there, that's going to be energy, and the units are going to be in joules. It's simply going to be the mass of whatever we're working with multiplied by the latent heat, and this can be for both fusion, if I put an F there, or I could also put a V there and say it's for vaporization. Both are going to apply. Now let's talk about solving problems. First question you're going to ask yourself, is the system isolated? And you're always going to say yes. What we then do is we apply the conservation of energy, and we say that the heat in is going to be equal to the heat out, keeping in mind that one of the two of these is going to be negative. And again, I prefer just to say that the sum of the Q's is equal to 0 and let the negatives work themselves out. If there's no phase changes, then very simply we say that the heat involved is going to be the mass times the specific heat times the change in temperature. If there are phase changes, then what we have to do is we also have to say, well, there's also going to be some heat associated with the phase change, which is going to be the mass multiplied by the latent heat. And you can kind of take a look at the temperatures, typically of water, and know if there's going to be a phase change, and whether it's fusion or vaporization. And what this number 5 kind of applies for is temperature changes being positive. That's only if you're going to say that the heat in is going to be equal to the heat out. You have to essentially kind of stick a negative sign in there. If you work it the way that I prefer, which is sum of Q is equal to 0, you don't have to worry about that. The negative signs will take care of themselves. One thing to kind of keep in mind is there's only going to be one temperature final. All objects are going to have the same final temperature, and then kind of solve a big algebraic mess. And I'll work some problems in the solved problems for you to kind of see the thought process here. So now let's change gears a little bit and talk about how heat is actually transferred. We're going to talk about conduction, convection, and radiation. First, let's talk about conduction, which is going to be the case where there's going to be some contact between the two materials that are exchanging heat. Essentially, we can kind of think of it as we have a hot region over here and a cool region over here. So here we have these atoms, and we'll say they're maybe vibrating back and forth, and I'll make them draw them vibrating back and forth with very large amplitude because they're very hot. And here we have a cool region where the molecules are not vibrating very much. Essentially, these molecules are going to bump into these molecules and transfer some energy to them. And so the heat flow is always going to be from hot to cold. Very important concept here. We're never going to have heat flow naturally from cold regions to hot regions. The amount of heat flow per unit time can be given by this equation right here, where this is going to be energy in joules. This is going to be time in seconds. You can kind of see that the unit associated with this side of the equation is going to be a joule per second, also known as the watt. That's going to be equal to some constant, which is related to the thermal conductivity. I'll talk about that in the next slide. Essentially, what is the temperature difference? If the temperature difference is very large, heat's going to flow fairly rapidly. If the temperature difference is close to 0, no heat's going to flow. It's going to be related to kind of the length of the object that's connected them, as well as the area. Kind of think of this as maybe a hose that's letting heat kind of squirt through it right here. Obviously, if we increase the area, it's going to increase the flow of heat. If we decrease it, it's going to decrease it. And you could make a similar argument for the length. And these thermal conductivities are given, this is something you kind of look up in a table, 14.4. So it's going to be the table of thermal conductivities. Essentially, you can kind of see different materials are going to have different thermal conductivities. For example, silver is going to be 420 joules per second meter degree Celsius. On the other side of the spectrum, we're going to have, for example, air. Air is going to be much smaller thermal conductivity, and so what that says is this guy right here is a very good insulator, and this guy right here is going to be what we call a very good conductor. Because all of this comes from free electrons, metals are going to be good conductors of electricity and good conductors of heat. Insulators are going to be poor conductors of heat, and they're also going to be poor conductors of electricity. Now, if you go down to the hardware store, you're not going to see, thermal conductivity on fiberglass insulation. You're going to see what's called R value. Essentially, all the R value is how thick is the object. So that's going to be kind of a length or a thickness divided by the material. So here we kind of have maybe some material, it's got some length associated with it, and the R value is just going to be the ratio of the length to the thickness. So we can kind of try to take a look at some heat flow through this guy, and just some R values. Glass is going to have a fairly low R value compared to, say, fiberglass insulation. Convection is the next type of heat flow, And essentially it doesn't require necessarily contact. What it's going to rely on is the fact that hot air or hot water is going to have a different density than cooler water or cooler air, and so we're going to have some mass movement or some natural mixing due to this. It can be natural or forced. Both of these examples are natural, where here we have a heat source. We're going to have some conduction through the bottom of the pan. Now we have some hot water. This hot water has a different density than the cold water, and so it's going to tend to rise. Remember, less dense things tend to rise. And then we're going to kind of get a cycle right here where the cold air sinks, gets heated up, and so on and so forth, so we can reach our equilibrium temperature much more efficiently. Same is true for kind of old school houses with radiators. Here we have some heat source. It's going to warm up the air, so we're going to have some hot air. Here we're going to have some cold air. We all know that hot air rises, and so we're going to kind of get a little cycle like this. You want to make a radiator work better, you blow a fan across it. That's going to be an example of forced convection. And many homes nowadays have a system like this where we have a forced hot air that's going to blow air out of the registers, not really relying on natural convection, but more of a forced convection. Same is going to be true for a body temperature. Another example of forced convection is going to be the wind chill. For example, if I have a person right here, it's a very poor person, they're going to be fairly warm. They're going to warm up the air all around them through contact, and then the cold wind is going to kind of come in and carry away all that warm air, making the person feel much cooler. The last type of heat transfer is going to be through radiation. Most common example that you all may kind of think about would be the sun. The sun is at some temperature and it's going to be irradiating us with light. We're going to be able to lay out in the sun and feel warm. And with this particular example right here, the sun, we don't need a medium in which to operate. So radiation does not require any physical contact of any kind. The sun's light rays can propagate through space, empty space, which is a vacuum. Now, of course, I have to take the beauty out of it and put equations to this. How much energy is going to be radiated? Well, this is going to be, again, some energy per unit time, so a joule per second, or how many watts of power we're talking about, is going to be related to this side of the equation right here, where this is going to be, where this little e is going to be the emissivity. This is going to be some Stefan-Boltzmann constant, which is just a constant, 5.67 times 10 to the minus 8th. See the watts per meter squared, Kelvin to the 4th. This is going to be the surface area, so make sure we don't confuse this with the cross-sectional area, which we saw in conduction. And then this is going to be the temperature to the 4th, and keep in mind that temperature must be in Kelvin for this equation to work out. This emissivity is going to actually be a value between 0 and 1, characterizing how well it actually emits. Black objects, or black bodies as they're called, typically have an emissivity near 1. So if you read a problem and it doesn't give you an emissivity, it just says it's a good radiator, then what you do is you set emissivity is equal to 1. That's a good radiator. Shiny objects or white objects are going to have emissivity near 0. So again, taking the beauty out of getting a suntan, suppose I wanted to talk about the rate at which I'm warming up because of the sun. So I've kind of rewritten the equation from the last slide. I've just kind of grouped sigma t to the 4th over here. It's actually also going to matter whether you're directly parallel or directly perpendicular to the sun's radiation. So for the sun right here, sigma multiplied by t to the 4th is going to be 1,000 watts per meter. So that's going to be these two guys for the sun, multiplied by your emissivity, multiplied by your cross-sectional area, as well as the angle that they come in. Obviously, when that angle is equal to 90, you're going to warm up the most. If a problem doesn't give you the angle, you assume that it comes in perpendicular to the surface, and straight up use the equation from the last slide. This cosine theta is going to be responsible for the seasons. Contrary to popular belief, the Earth is not closer to the sun in June than it is in December. It's actually almost a perfectly circular orbit. What it comes from is from this tilt, this 22-degree tilt that we have. In June, the northern hemisphere, essentially we could say the angle is going to be small, close to zero. However, when the northern hemisphere experiences summer, the southern hemisphere down here has the sun coming in at a very oblique angle, and so they receive less radiation, so it's actually going to be winter down there. And the reverse is true. The northern hemisphere is going to experience winter in, say, December, while the southern hemisphere is enjoying suntans on the beach. And the last few slides are for summary, and again I'll just page through them.